In this video, in our ladder diagram series, we are going to learn how to create the basic logic operations known as AND and OR, that in LD are also known as series and parallel. We will see how they work and then we will move on to an example. So, logic operations or logic gates are typically represented by truth tables, meaning tables that show for all the combinations of the inputs what will be the output. Let's jump into it. In an empty CoDeSys program, I will create three variables. The first one will be input A, input B, and output C. These three will be our variables for our examples here. Let's start now with the AND logic. This is used when all the conditions must be met to activate an output. So for our logic table we will have input A and input B. This should be our output C. This means that if both are false, output C will be false. If even one of them, either A or B, is false, output C will remain false. And output C will only be true if both input A and input B are true. And to do that, in the ladder diagram, we need to use what is known as a series. We can create two normally open contacts and a coil here in CoDeSys. The first contact will be input A. The second one will be input B, and the coil will be output C. In this way we have created a series that is exactly an AND operation, because current will flow to output C only if both contacts are closed, because if even one of them is as in a variable that is false, as associated a variable that is false, current will not flow at all. Now let's go online and see it. Then I will run and I will use Ctrl F7 to force values into our Boolean variables. So right now both A and B are false and output C is false. Let's try all the combinations. So if I only input A is true, output C will remain false. Let's do the opposite. If only input B is true, output C will remain false. But instead, if both input A and input B are true, output C will become true. This is exactly an AND logic gate. And you can see that we can achieve the evaluation of multiple conditions at the same time. The output will activate only if all conditions are met. We will see an example later in the video. Now let's delete this network and create a new one. Let's now move on to the OR gate. So in this case, we can see the truth table that we want our output C to be true if either input A or input B are true. If one of them or both of them are true, our output C will be true. If both are false, output C will be false. And to do that in a ladder diagram, we achieve this result with a parallel. So again, I can place a contact here. Then I can right click just before the contact and select Insert Contact Parallel below. As you can see, we have created some weird thing here, a parallel of contacts, and then I can place a coil at the end of our parallel. If you see the option grayed out, you can simply select the network and click on Insert Coil. Now let's set our variables to input A, input B, and output C. So in this example, you will see that output C will become true only if current is flowing to this point over here. And current will flow here if either input A is true or if input B is true. Just one of these two is enough to get power flowing over here and reaching output C. Now let's go online and see it for ourselves. Both input A and input B are false, therefore output C is false as well. Let's set input A to true, and you can see that output C is becoming true as well. On the other side, you can set input B to true and input A to false, and you can see that output C remains true. And if I set both of them to true, output C will be true as well. This is an OR operation. It is a parallel, and this is used when you need just one condition out of many to set an output or to do something. Now let's go offline, let's remove our network, and let's do a simple example. Let's remove our variables and let's do an example where we have a few inputs and a single output. So let's say that the output is the motor running. It is a Boolean variable that will control the movement of a motor. And in our machine we will have a start button, a stop button, an emergency button, and we will also have some signals for some safety guards. Safety guards closed. Now we will need to use logic gates and also set and reset coils to create the logic for this operation. So we want to set the motor running when the start button is pressed, but at the same time we do not want the stop button being pressed. We want the emergency button to not be pressed as well, and we want the safety guards closed. And since we want many conditions at the same time, we can achieve that with a series. So let me first place a coil, and I want this coil to be a set coil. So I will right click and say insert set coil, remove the one that I placed, and I will place the motor running variable. In this way, we will set the motor running to true when current gets to true here. And to do that, we want our start button being pressed, our stop button not being pressed, our emergency button not being pressed, and our safety guards closed. So let's start and create our series. So first we will have start button with a normally open contact, because we want this to be true to start the motor. Now we can insert a normally closed contact. I can place it here, normally closed. This will be for the stop button, because we do not want the stop button being pressed. Then for the emergency button, you should know that typically emergency buttons are normally closed. So when you are evaluating some digital input, you will see them being true if the button is not pressed. So we want them to be true, and this for us is a normally open contact. So emergency button, emergency. And then we want also the safety guards being closed. So another normally open contact with the safety guards being closed. These are the conditions to set our motor running. Then we need the opposite for stopping it, because we want either one of these conditions to stop the motor. So if the stop button is pressed, we want to stop the motor. If the emergency button is pressed, we want to stop the motor. And if either safety guard is open, we want to stop the motor as well. So either one of those conditions. So this is an OR operation. So again, let's start by placing our reset coil with our motor running. And then let's create our parallel. I will first place a normally open contact for the stop button. So if the stop button is pressed, we want to stop the machine. Then we want the emergency button being pressed, and this is negated. So I will right click over here and I will select insert negated contact parallel for the emergency button, and then I will also create another parallel for the safety guards closed. So we want to evaluate if the safety guards are open. So again, a normally closed contact. Right click and insert negated contact parallel with the safety guards closed variable. Let's go online and try it. So right now the motor is not running. You can see that over here. And let's reset the emergency button and the safety guards. So both are true. This means that the emergency button is not pressed and the safety guards are closed. You can see that these three contacts become blue, so power would flow through them, but we do not have the start button. So if we press the start button, you can see that now motor is running. And even if I release the start button, motor will keep running. Now if we remove either one of these conditions, the motor running should become false. Let's try it. We can press the emergency button. You can see that now current flows through here and the motor running variable has been reset. We can try it in the same way again with all the other variables to stop the motors. So if I restart the motor and I press the stop button, motor running becomes false. And let's do it again for the safety guards closed as well. Now the motor is running. I will release the start button and set to false the safety guards closed. Motor running has become false again. So as you've seen, real machines rarely use a single logic gate. They use a combination of them or multiple instances of them. So this is the basic component to evaluate multiple conditions and to make decisions. And with ladder logic, it is quite easy to visualize the logic being implemented through the visualization of the power flow.